Okay, we've done specific heat capacity. We've learned about the equations. Now let's look at an example where we basically are using this equation. And the equation the example we're going to do is essentially finding the thermal equilibrium of water. Okay, so let's have a look at the example. So a quantity of 300 grams of water at 20 degrees Celsius is mixed with 600 grams of water at 80 degrees Celsius. The mixture is stirred and its temperature is measured. Determine the temperature of the mixture. Okay, so just draw a quick picture. So here we have, two temperatures. So we have 300 grams at a cooler temperature. So I'll make that, even though 20 degrees isn't that cool, I'll make it blue to make it cool. So 300 grams at 20 degrees Celsius. And a bit warmer, we have at 600 degrees Celsius, so double the amount at 80 degrees. Oh, there we go. At 80 degrees Celsius. Okay, and what we expect is that this has more water. This is a higher temperature, okay? Heat's going to transfer from the warm to the cooler. Now there's less water here, so there's less water to reduce the temperature of this. So we expect it to be closer to 80 degrees Celsius than to 20 degrees Celsius. So how close is it going to be? Well, let's look at the two situations. Each has, let's call this mass 1, and let's call this mass 2. Okay, well, the equation for specific heat capacity is just the heat is the mass times the specific heat capacity times the change in temperature. Okay, and so let's have a look at this. So here we have Q of mass 1 is equal to Q of mass 2. So we write that down as at mass of 1, C, which is the specific heat capacity of water, times the change in temperature. So we have the temperature, whatever the final temperature is, minus 20, okay? So the higher temperature minus the lower temperature. Okay, now the reason we could reverse it, okay, and put 20 minus T, but it's going to give us a negative value. So we want to make it a positive value all the time, okay? Because in this example, basically heat is being gained, okay? And now if we go to the other side of the equation, we have mass 2 times specific heat capacity. And here now we have 80 minus 80, there we go, minus the final temperature, okay? So final temperature minus 20 degrees, this is going to give us a positive value, and 80 minus the final temperature, this is also going to give us a positive value, okay? So the temperature lost, or the temperature gained by mass 1 is equal to the temperature lost, or the heat lost, gained by mass 2. That's why the two are equal. If we do notice that the specific heat capacity is water for both, and so we really don't need this in the equation. Okay, we cancel it out. Formally, to do this, we divide each side by C, and you can see that C divided by C is 1, and they cancel out. All right, so let's substitute some values in here. So mass 1 is 0.3 times T minus 20. Now I'm gonna avoid putting units for now. You should put units in just because it helps you see what units your final answer are going to have. But because we're asking for the temperature, we know it's going to be degrees Celsius. If you want to be a bit more formal and more careful, you can put units. This is a quick and dirty example, so I'll just skip it for right now. Okay, so 0.600 kilograms, just substituting values in now, 80 minus T. Okay, and now we basically need to isolate for T, and so we multiply this, distribute, so 0.3 times T, 0.3 times minus 20, 0.6 times 80, 0.6 times minus T. So I'm going to skip a couple steps here, and I'm just going to go to an intermediate step. If you want, you can go through all steps to see where I get this answer from. But what we are going to have is 48 plus 6 Okay, and that's what we get from 0.3 times 20 is 6, 0.6 times 80 is 48, equals, and now we look at the temperature side of things. So we have 0.3 and 0.6. If we move all that to one side of the equation, what we get is 0.900 times the temperature. Okay? And just one more step. So the temperature is equal to, so we add these up, 48 plus 6 is 54. And now we want to isolate for T. To do that, we divide both sides by 0.9. So this is 54 divided by 0.900. If you want to keep track of the units you should see right now are just 54 kilograms degrees Celsius divided by 0.9 kilograms, and that's what you get from all these intermediate steps. And that gives us a value of 60 degrees Celsius. Okay, so it is closer to 80 degrees than 20 degrees, which we predicted. And this is how you find basically where it reaches thermal equilibrium. And when it reaches thermal equilibrium, you just start at this point here. So the heat, essentially what this means is the heat lost by one body is equal to the heat gained. And now we have equations where we can relate heat, and from there on it's just going through the mathematics to get our final answer. Okay, hopefully that was helpful and hopefully you understand now.